Okay, thank you, Jim, for your invitation, and also for the kind introduction. And as he said, I'm also working on the structure of photosystem 2 and the mechanism of water oxidation. And I will introduce what we have obtained based on our structure analysis. I will skip this. And this is the so-called state transition cycle of water oxidation. And we have, Jim has reported its structure of PS2 at 3.5 angstrom resolution in 2004. And we, in 2011, reported its structure at 1.9 angstrom resolution, which is a dimer consisting of 40 subunits with a molecular weight of 700 kilodalton. Since we are focused on the water oxidation, we also focus on the structure of the manganese cluster, which is located here. And from our high resolution structure analysis, you can see clearly the structure of the cluster in each atom, the location of each atom, which is composed of 4 manganese ions, 1 calcium, and coordinated by 4 water molecules directly. 2 of the water molecules are coordinated to the calcium ion, and the other 2 water molecules are coordinated to the one of the manganese ion, manganese 4 here. There are several water molecules surrounding this cluster, which forms extensive hydrogen bonding networks surrounding this cluster, which may be important for proton transfer. And of course, it is coordinated by a number of amino acid residues. These are the coordination patterns for each of the metal ions. Because we are focusing on the mechanism of water splitting, I will also focus on the structure of the metal catalyst. If we remove all the amino acid residues and just looking at the structure of this metal cluster, you can see it is look like a distorted chair form. And this kind of distortion suggests that this structure may be somewhat unstable. And we think this is one of the most significant features for this structure to be able to undergo structure changes easily, because it is distorted. And since we reported this structure in 2011, there are extensive debates on the manganese distances and the manganese oxygen distances. The distortion caused, one of the major factors causing this distortion is the position of O5 here. You can see its bonding distance to these manganese ions are in the range of 2.5 and 2.6, and these distances are extremely longer than the typical manganese oxygen distances, which are in the range of 1.8 to 2.1 angstrom. And this causes the distortion and also causes the unique position of O5 here. But since we reported this structure in 2011, there are extensive discussions on the distances between manganese ions. As you can see here, we reported this distance in the range of 2.8 to 3.0 angstroms. But the exact results, as well as theoretical calculations based on our structure, suggested that these distances may be slightly shorter, which suggests that our structure may have suffered from radiation damage, causing the reduction of manganese ions in the cluster. This may also cause the changes in the position of O5. As I mentioned, this has a unique position, but if there is some radiation damage, we may be not sure about its position. Although we have obtained electron density, which is very clearly shows the position of O5 here. You can see this is manganese 1, this is manganese 4, and it's sitting in middle between these 2 manganese ions, and it's apparently longer distances in this bond length compared with the other oxygens. They are very close. So in order to remove the radiation damage, we performed X-ray deflection experiments using the XFEL, X-ray electron laser, which has a time of duration of 10 femtoseconds. And within these 10 femtoseconds, the X-ray radiation caused the structure changes will still not occur. So we can collect data before the structure is changed by the X-ray radiation damage. And we skip this, and we obtained the structure of the cluster at 1.95 angstrom resolution with the 10 femtosecond X-ray electron laser. And as you can see from this structure, we can locate each of the atoms very clearly based on their electron density. And we determined the distances, which is here, for example, it's 2.7 compared with the previous synchrotron X-ray radiation structure. It's 2.8. So it's very slightly shorter than the previous structure. It's also 2.7 compared to 2.9 angstrom, and 2.9 compared with 3.0 angstrom in the previous synchrotron radiation structure. Then we look at the position of O5 again. It's here, the distance to these two manganese ions became 2.3 and 2.7 compared with the previous 2.5 and 2.6. It's slightly changed, but you can still see that the position of O5 is very unique. It has very long distance compared with the other typical oxo bridge oxygens. So this suggests that O5 binds very weakly to the nearby metal ions, and in turn may suggest that it may participate in the water splitting reaction to provide one of the substrate oxygen atoms here to make an O bond. So this suggests that O5 is the reaction site for the formation of O bond from the structure. And as Jim also introduced that in 2015, my colleague Dr. Zhang, he will talk his structure, I think, compound later in this meeting. He succeeded in synthesizing a compound, manganese 4 calcium, which is, it's very similar, has a very similar structure with the catalyst in PS2 we solved in overall structure. But if you look at the structure detail, if you compare them very detailed, you can see there are two major differences. One is the bond length between O5 and the nearby metal ions. We saw a longer distances, but in this synthetic compound, the distance is usual, is normal for manganese oxide. And then the second difference is that we saw O5 here, but there is no O5 in this synthetic compound. But I would like to remind you that in this synthetic compound, this O5 is replaced by a carboxylate. There is oxygen here, but it is a carboxylate coordinating these two manganese ions instead of oxo bridge oxygen. So there is still oxygen here, not absent in this structure. And we continue to think of the mechanism of O bond formation, as I suggested that this O5 site may provide the reaction site for O bond formation. Then if you look at the structure surrounding this O5, we can see there are two water molecules. One is coordinated to the manganese 4 ion, and the other one is coordinated to the calcium ion, which are in the hydrogen bonding distance with O5 here. So this area containing 3 oxygen atoms may form the reaction site to provide the O bond oxygen, molecular oxygen here. This is based on the structure we solved at S1 state, which is the dark stable state before reaction starts. And based on this structure, there may, in addition to this possibility, there are many other possibilities which have been suggested regarding the mechanism of OO bond formation. And even with this possibility, there are 3 oxygen atoms, so we still do not know which of the 2 oxygen atoms may form the OO bond in this region. So there are many possibilities. For example, there's maybe one water molecule come in to this site or the other site, close to the O5 oxygen to form an OO bond. Or this new water molecule may come from one of the 2 water molecules, as I mentioned. And finally, this, I think, is another mechanism which may not involve the OO bond, just between these 2 water molecules, because they are also in the hydrogen bonding net distance. So we have to distinguish these mechanisms experimentally. Although Per Sigman has told us his theoretical prediction and results, we want to confirm from the experiments where and how the OO bond is formed. So because we just solved the structure as one state at high resolution, we needed to know several of these intermediate structure experimentally. And we focused first on the S3 state here, which is formed by 2 flash illumination starting from S1, because S3 state is the metastable state immediately before OO bond formation. So from S3 state, if you give 1 photon, it will proceed to S4 and immediately to S0, then evolve 1 molecule of oxygen. So we focused on the structure of S3 state. In order to solve the structure of S3 state, we used the pump probe approach and the time-resolved experiments by providing crystals first with 1 flash. In order to obtain high efficiency, we provide 1 flash from 2 sides of the crystal. Then after 10 milliseconds, we give a second flash to the crystal. Then after 10 milliseconds, we give a XFE, X-ray free electron laser pulse to obtain the X-ray free diffraction date. Then because there are 2 reasons we needed to use very small crystals. One is in order to get very high efficiency of S3, we needed to use a very small crystals. The other one is that every XFEO pulse will totally destroy the crystal. It's very strong, so we cannot use the same crystal. So we use so-called serial femtosecond X-ray crystallography, and by flowing the crystal continuously from upside to downside with very small crystals, and we illuminate here with 2 flashes separated by 10 milliseconds, and then illuminate with an XFEO pulse after 10 milliseconds of the second flash. You can see only the laser flash. You cannot see the X-ray pulse, but we are continuously using the 2 flashes and 1 X-ray, 2 flash and 1 X-ray pulse. So these are the crystals we used. They are very small, so they can be excited efficiently. And this is one of the image of the X-ray diffraction data we obtained with 1 pulse of the 10 femtosecond XFEO. And we collected several data sets in order to obtain the reproducibility. And we just focus on one of them. And what we did is we calculate S3 minus S1 Fourier isomorphous Fourier difference map, which means that we subtract electron density with S3 from S1. So we can see only the structure changes occurred induced by 2 flash illumination. And we saw this is the whole piezo-dimer, but we can see only those areas with structure changes. And this electron density indicates where they the structure has changed. And the other area, you can see there are no electron densities, which means that the structure remained unchanged. And I will explain very briefly how this works. For example, there are three patterns. One is that if the atom here is, the structure is slightly changed and moved to this position, the electron density initially is here. After two-flash elimination, the electron density is here. So when we do A2 minus A1, you get a minus electron density and a positive electron density, which means that the atom is moved from minus to positive electron density slightly. There is another situation that if this one of the atoms initially located here, it's moved or disappeared somewhere, then we get a minus electron density. Or alternatively, if there is nothing here, but after two-flash elimination, one atom comes into here, then we get positive electron density. So from this, in order for this isomorphous Fourier difference map approach efficient, we needed to ensure that the two data sets from the two crystals must have a very high isomorphicity. This is expressed by the R-iso between the two data sets. And these are the numbers of R-iso we obtained with our two data sets. One is dark, and the other one is after two-flash elimination. You can see they are very low number, which means that these two data sets have a very high isomorphicity, so which makes the isomorphous Fourier difference map approach effective. Otherwise, you will see a lot of noise electron densities. So I'll come back to this Fourier difference map. We saw three areas of structure changes. Here, one is here, the second one is here, and the third one is here. Then I will skip this. The first one we saw is that minus electron density located close to YD, this tyrosine residue, which means that something has disappeared, or I should say it's become flexible or mobile, so it cannot be seen in the X-ray crystal structure. And in the S1 state structure, there is a water molecule here, which has two positions, occupied two positions. And after two-flash elimination, this water molecule moved to slightly farther away from the YD. This water molecule originally is hydrogen bonded to YD, but after two-flash elimination, this hydrogen bond was broken, suggesting that proton transfer may have occurred through this YD to break this hydrogen bond. Okay, skip this. And the second structure changes we observe is around the QB electron acceptor. Here, there is some positive electron density and a negative electron density. So this QB ring, QB molecule is rotated slightly in this direction, making hydrogen bond. This hydrogen bond is originally hydrogen bonded, but after two-flash elimination, this hydrogen bond becomes shorter, so making this hydrogen bond stronger. This suggests that after flash elimination, some negative charge remained in this QB because we collected data after 10 milliseconds of the two-flash. So QB partially becomes QB minus, and this hydrogen bond becomes stronger, because it is minus, and there is some slightly partial positive charge in the histidine residue. The final, I will skip also this. The final structure changes we saw is, of course, around the oxygen involvement center, the metal cluster. Here, you see there are a lot of structure changes occurred in this region. And one, for example, is here, minus positive, means that this magnetized, this is magnetized 4, moved slightly from here to here. And there is also some structure changes in this amino acid ligand residue. and somewhere here. But there are two most important structure changes. One is this green electron density, which is positive. It does not have a pattern of negative electron density. So this means that there's something appeared in this region after two-flash illumination. And here, this water molecule, has a minus electron density, suggesting that this water molecule has moved somewhere else or become mobile after two-flash illumination. And this water molecule is hydrogen bonded through another water molecule to O4. And there's a hydrogen bonding network connecting this O4 to the outer surface of the protein complex. So we think that after two-flash illumination, this hydrogen bonding network, there must be some proton transfer through this hydrogen bonding network, leading to the break of this hydrogen bond here. Then this positive electron density, we can model as a new oxygen or water molecule here. And it's very close to O5 position. We reported its distance is 1.5 angstrom, but we think this resolution, we have reported resolution at 2.35 angstrom. So we have some experimental errors in this distance. We are not sure, but there's definitely a new oxygen here, close to O5, that is able to form an O bond between this oxygen O5 and this new water molecule. So overall, the structure changes occurred from S1 to S3, is that this is the structure at S1 state, and after two-flash illumination, there's a new water molecule, or oxygen, come close to O5 to make an O bond in this cluster. Okay, I think, and this situation in PS2, if you took this bond out, it's manganese 4, O5, O6, and manganese 1. You can also see a very similar situation in the cytochrome C oxidase in the final intermediates. In the structure of cytochrome C oxidase, you can see there's copper, B, and ion center. Between these two metal ions, there's the two oxygen, which forms a superoxide. But they catalyzed the just opposite reverse reaction. One is water oxidation, and one is oxygen reduction. Okay, I will finish this by just thanking. Okay, I'll skip this. My colleagues who are involved in this work, and the crystals and the structure analysis are conducted in my laboratory. The structure is solved and analyzed by Dr. Sna, who is an associate professor in my laboratory, and he is also in the audience and has a poster in this meeting. And we are collaborating with Dr. So Iwata for the femtosecond FEO experiments and with other people. With this, I would like to thank you for your attention.
Thank you very much. And of course, these X-abstract experiments are very difficult, and you're doing a fabulous job. We're going to have another lecture on experiments on PS2 after the coffee break. Now, what about some questions now for?
Yes, you had a short distance between the oxygens in S3, but I didn't hear, and as I understand, you don't have it anymore. You have a longer distance. Is this secret results or no?
Yeah, we analyzed several other data sets, and we actually obtained a slightly longer distance, but we haven't published it.
Oh,
yeah,
slightly longer.
Slightly. We haven't published, but it's longer than 1.5.
What was the reason you had the short? Was it low resolution or different?
The low resolution, and yeah.
Did she? Oh, sorry.
After the insertion of O6 in our term, what is the distance between O5 and W2?
O5, excuse me?
O5 and water sitting on the manganese floor. W2.
W2 does not change its position, so it's the same. We
But
don't
after
see change.
insertion of O6, the O5 must move away from the manganese. And the
No,
distance
it's,
between the water sitting on the dangling manganese and the O5 must be shortened. Am I right?
No, the O6 is inserted, it's not in the linear position.
Yeah.
It's in somewhere outside of
But
the...
push the O5 away from the cube.
The position of O5, we also see very slight changes. We cannot, at this resolution, we cannot see definitely how
I
much
become
it's
really skeptical for ore bond formation between O5 and O6. In our new proposal, I'm going to present you today, tomorrow. I don't suggest the ore bond formation between O5 and O6. Rather, the O6 is the successor of the O5.
Okay, we'll hear about that tomorrow. Lily. Oh, no,
Could you explain why do you observe so sharp difference with the Berkeley group at almost the same time for using the same using XFEL?
I would suggest you hear the Berkeley group's talk after this session. I think we come almost to the same conclusion, as far as I know.
Another question.
after coffee.
Okay. Another question.
Yeah. So I think in S1 and S2, well, S1 it's quite easy to move the O5 like to an open or closed cubane. Well, again, then S3 seems to be more like just one structure. So wouldn't you, in principle, predict that you would have a shift of electron density from something that has two populations?
No. I would comment on this question is that the structure we experimentally are solving is only one type of structure. And we must fix the structure at one state. Otherwise, we cannot distinguish.
Sure,
So
but
we always see only one type of structure.
Yeah.
And theoretically, you may see different kind.
But you have more than one molecule, and if they are in a
No.
Boltzmann population, you will see a density will be averaged between
no,
two
we don't
states.
see in our experimental condition. And I think that the two structures depend on the condition, the solution condition. And if we choose the solution condition which has two structures mixed, we may not be able to solve them clearly in the experiment.
Okay.
Theodore, without any...
You mentioned amino acid changes in this structure, and of course you have other structures. I'm wondering what are the largest changes you've seen?
Yeah, I just did not explain this slide. The most significant changes we saw is this amino acid residue. This is glutamate 189. Changes from this position to this position. We changed the 0.5 angstrom. And the reason why this changes is that when O6 comes in to this position, if this residue does not change, it has a distance to O6 of 2.3, which it's too short for O6 to be able to come into this position. So this residue moved away from its position by 0.5 angstrom to enable O6 to come into this position, which now has a distance of 2.7 angstrom.
Yeah, that's a very large change, and then I guess going back to Gary's comment for the previous talk, those sort of changes, especially if they're in the coordination sphere of manganese. I mean, we typically focus on the cluster because, of course, that's where the exciting chemistry happens. But if the ligands push away or push in, that will change spin states and reduction potentials and will affect a lot of aspects.
Yeah,
at least from my perspective. So it'd be good to have this emphasized for us who read the papers.
Yes, just a comment after the question of Ville. If we call S3 the state which is formed by two flashes, you have heterogeneity. You have at least two different S3 configurations. So that should be considered. You have one which gives the APR signal, and the other one which does not give an APR signal, at least until now. So that it should be. I don't know what it is, but one is what I say defined by sensitive to near infrared light because we induce another state. But certainly there is a second S3 invisible state, and the Professor Yamaguchi also had many papers on that, on different configuration in S3, so, but he does not want to talk about.
Okay, I'll ask you one question. So you see a density, in the difference maps, you see a density which you now call O6, and you don't really know if it's an oxygen or not, but it looks as if it could be water or something like that. And can you quantify it at all? Is it in the noise level, or is it way above the noise level? Does it correspond to one whole molecule?
Yeah, the noise level, I did not, at the noise level, you can see that in other areas there's no noise. This compared with the whole PS2 dimer. This is the whole region of the PS2 dimer. Yes. And there's no, the noise, maybe this may be noise. Yes. These are the noise. But
I'm talking about the difference map. In the difference map, you show a difference, which you say is O6, yeah?
Yeah. I'm
not saying it isn't, but can you quantify in terms of what the signal size you would expect if there was a water molecule there? Is it possible to calculate that and then look and say, well, yes, this is from a quantitative point of view, this difference is equal to one water molecule, or it's not?
Yeah, first I would say we cannot distinguish in the X-ray structure water molecule between water molecule and oxygen.
Yes, yes, I understand that. Sorry, I could say anything. Oxygen.
And the electron density, you see, when the water disappeared here, it's negative electron density. And here we saw positive electron density. So the positive electron density is even larger than this negative electron density. So it's comparable with water molecule or oxygen.
Okay. Yeah. All right. Look, we haven't been terrible chairman, but we could get a coffee. I think we can't help it. We can't be back by 3:30. That's impossible. But let's try to do it in 15 minutes and come back at 35, 25 to